Hi, good morning, everyone. Good evening. This is the weekly contributor call of OpenEBS. Today is 5th October, and we're going to have two topics for today's call. One is Prometheus and OpenEBS, how OpenEBS can help as a local storage for Prometheus. And the other topic is about one of the components of the recently released storage engine called CStore. Vita is going to cover the details of CStore replica. To begin with, I'm just going to talk about how OpenEBS can be used as a local storage for Prometheus and why it should be used, and what about scalability and all. With that, let me just go a deep dive into the solution of using OpenEBS with Prometheus. The general agenda is going to be a short session, about 15 minutes. Probably we will do a detailed video of the entire solution pretty soon. But today's talk is going to be kind of an introductory type, right? So, and also we recently published a blog earlier this week on the same. It's on the OpenEBS publication on Medium. Feel free to take a look at it. So most of the contents are going to be around the same blog. So let's just talk about storage for Prometheus and what are the different types of storage, and generally what are the philosophies behind it. Prometheus is a great monitoring tool, almost number one in the Kubernetes community. It has very large usage. And then the typical deployment of Prometheus is you have multiple namespaces in a typical cluster, and you have applications running. Prometheus runs on a pull model. So Prometheus servers are deployed inside the cluster, and Prometheus is going to pull the metrics from each application pod, scrape them, and store them in storage, whether it could be local or it could be a remote storage. Remote storage is it has a different functionality, working functionality compared to the local storage. Local storage is supposed to be simple. Most of the people understand local storage as local disk. When you use local disk, yes, there are some problems, but there are solutions like OpenEBS which can be used as local storage for Prometheus, which is what I'm just going to talk about now. When using remote storage, Prometheus does not control how and how to write into remote storage, how to read from remote storage. It's left to the implementation of the remote storage, but it is given a standard API in terms of a remote storage adapter to write the Prometheus metrics into that adapter, right? The remote storage can be a hosted service, or it could be an on-prem deployment along with the basic stateful application databases applications like Cassandra and all that stuff. The idea is the remote storage is scalable, and Prometheus does not control it. The only thing that Prometheus controls and has code for it is the local storage. And then Prometheus is always deployed as a deployment, which really means that it has a kind of a limitation into how much traffic it can take, either in terms of read and write. So typically in large clusters, you will see more number of Prometheus servers deployed. For example, in this case, I've taken application pods in namespace 1, and namespace 2 also is supported by the same Prometheus server. But as you increase the number of metric sessions, pull sessions, It could be that there is a different Prometheus service or server that's pulling out the data from those different pods. So it will have a different local storage, but it could write to the same remote storage even if there are multiple Prometheus servers. So remote storage services for Prometheus are typically called horizontally scalable. That's because multiple Prometheus servers can actually write into the same storage, and then you can pull the metrics out of that storage from one single control panel. So that's a bit of an introduction of how the storage is deployed either in terms of local or remote. When you consider local storage as local disks that are attached to a given node, there could be some limitations. Let me just walk through the differences. Right. Local storage has the time. Prometheus implemented TSDB, the time series database. They have simplified the format of the metrics to a level that it just takes only a couple of bytes to write metric transactions. And that's very powerful, and it scales. A single Prometheus server can support millions of transactions, right? And Prometheus local storage architecture also supports the concept of write-ahead logging in general. The idea is that you write for higher performance, Prometheus writes the metrics data into its own memory. And if you want to persist it, you can use write-ahead logging device into that node, and that's a great thing because there are some storage architectures which support WAL, and that can take advantage of this feature of Prometheus, right? And the general convention is that if local disks are used as storage for Prometheus, obviously the durability is not great because when you lose that node, the access to the storage is gone. They're not replicated, and there could be sometimes data loss because of a loss of the disk. So if you're using local disk, Prometheus local storage option is not really viable. It has to be considered only as an experimental setup, not production grade setup. However, Prometheus remote storage takes away the storage headaches or challenges from the Prometheus. It provides an adapter, and data is sent through the adapters, and the format of each third-party remote storage is different from each other. They're all custom made. And but the disadvantage of it is it's totally a different service. You need to manage them on your own, and there could be not free, of course, sometimes, and it's almost like a bigger setup than Prometheus itself. So OpenEBS is going to help simplify this storage requirements when used as local storage, right? And we talked about if you use local storage, local disks, then we have a problem of storage not being highly available. And another problem is, okay, you're writing metrics and you're running out of capacity. So how are you going to add capacity to the local storage on the fly? That's another perceived limitation. So these limitations, both of them are solved by OpenEBS. If you use OpenEBS as local storage, you won't have a highly available issue. The data is always highly available, no corruption whatsoever. And with OpenEBS, storage can be added dynamically on the fly, right? So let's look at how the highly available OpenEBS storage functions, right? So typically, OpenEBS is deployed as a cache storage, which really means that you're going to get a complete storage controller and replica functionality for each volume. So in this case, a local Prometheus server has a full featured storage controller in terms of OpenEBS. So there is a volume that's exposed to Prometheus, and then Prometheus accesses it as a iSCSI endpoint and writes into it. The data is synchronously replicated to three different replicas, which are spread across three different nodes, and sometimes this can be configured across zones as well, so that the high availability always exists even if one zone goes down. And then the next problem that we said we are going to solve is highly available, apart from high availability, is the expansion of storage on the fly. When you have a storage volume replica, it writes into OpenEBS replica, and replica really is going to write the data into the OpenEBS pools. And OpenEBS pool is a concept where the disks are abstracted out and presented as an object to the replica, which really means that you can add disks on the fly to the pool, and the replica does not even know that there is some additional operations available. Using the thin provisioning concept of pool, you can actually say that you have a lot of data storage availability, but in reality you can start with less number of disks, and as the data gets filled in, you can add more disks. This need not be local disks. It could also be a SAN storage. So for example, you can just start with few local disks and then add more when you need, or you can start with basic SAN storage and add one more storage SAN volume to it, right? And it could be a mix of both or a combination of both. So in terms of capacity, it's highly flexible and scalable as well. That's about why OpenEBS, and I'm just going to show how it's deployed. And in fact, we have deployed a live deployment for public access. The deployment that I'm going to show you is using Jiva as the storage engine. I just wanted to pick this example for its simplicity. And so as you can see, this is our E2E and CI workloads portal, where Prometheus is running as a deployment, which is one replica deployment, and it's running on node 2, and there is an iSCSI endpoint with 3 replicas. The 3 replicas are actually deployed on 3 different nodes, and the application is running, right? So but before that, I really wanted to show an example of the configuration. Let me pull up the YAML file that's used for this Prometheus service. So there's a config map here, and then let me go to the deployment. So in this deployment, the most important thing that we want to talk about is the storage, right? So as you can see, the volume mounts are pointing to one for the config and one for the actual store. It's configured to be at /Prometheus directory inside Prometheus deployment, and Prometheus directory is nothing but a PVC, Prometheus volume claim, which really comes out of Prometheus. Volume claim really comes out of the storage class called OpenEBS Jiva default. The Jiva default class, only thing you probably need to change is the capacity, how much you want. This gets stored in the replica container itself, which is a persistent storage. and you can change the request storage and use OpenEBS Jiva default, and then get the persistent storage without even having to have the additional burden of configuring the disks. So let me just go into a little bit of details of that. The persistent volume claim points to the storage class Jiva default, and you can adjust the storage as I just said. And then the storage class, you can actually see the storage pool is default, which is nothing but the storage that is provided by the orchestration system to the Docker container of a replica pod, a replica deployment, is going to be used as the persistent storage for that replica. That's the storage pool. In reality, if you want more scalable storage or a little bit more production grade deployments with more than 50 GB of storage, you can use a different storage pool that's built out of the actual local disks or SAN storage. So I just want to emphasize that it is the most simplistic local storage option available for Prometheus local storage TSDB. And let me show you why. Typically, when application is launched and the deployment, Kubernetes tries to use the local PVC and provision the persistent volume using the dynamic provisioner, in this case, which is OpenEBS. And the local provisioner, the dynamic provisioner of OpenEBS sets up an SKZ endpoint through the Jiva deployment controller, which actually is going to set up 3 replicas. In all these 3 replicas, the storage in this configuration is returned to /where OpenEBS directory, which is nothing but the local persistent storage of the container itself. And once this is all provisioned dynamically, the volume is mounted and the SKZ storage is mounted as a local directory here at /Prometheus, and your storage is available to Prometheus deployment. As you can see here, we've provided local storage, which is highly scalable as well as highly available, but we did not have to do any configuration. All we did is point a PVC with storage class as OpenEBS Jiva default, and we are all done, right? So that's as simple as it can get, and that's all I have. If there are any questions from the folks, I can take.